Good morning. Myself Tassnim Tamboli. Today's topic of ISE number 1 is Real World Accident Investigation, Stress and Deflection Failures in Aerospace Structure. Introduction. In aerospace engineering, stress and deflection plays a major structural safety. Even a minor failure in these parameters can lead to dangerous and disastrous accident. This presentation explores how much such failures occur in the real-life aerospace accident and what we learn from it. Importance of the aerospace structures. Aerospace structures are crucial for safety, performance, and efficiency, as they must withstand extreme forces while being lightweight. Their importance lies in enabling flight, provide necessary strength and durability to protect the occupants and payloads, in facilitating the aerodynamics efficiency through optimal design. Key benefits include enhanced fuel efficiency, reduced operating costs, and simplified maintenance, which are critical for both aircraft and spacecraft. Aircraft components like wing, fuselage, tail, and landing gear experience constant load. In solid mechanics helps engineers to analyze, predicts these stresses, ensure strength, stiffness, and stability of structure. Stress and deflection analysis. Here is the formula for stress, that is sigma F by A. So F is the force and the load applied in Newton, and A is the cross-sectional area of the material. This formula tells us how much internal force is developed per unit area when external force acts on it. In simple terms, if you push or pull something, the stress tells how much force easy for each tiny area is inside the material feels. Example in aircraft contexts is when an aircraft wing experiences lift, it bends upwards. The upper surface is under the tensile stress and the lower surface is under the compressive stress. Using this formula, sigma F by A, we can calculate the materials that are safely bearing the load. Second formula, deflection, that is delta FL cubed by 3EI. So here the F is the force applied, L is the length of the material, and E is the Young's modulus, and I is moment of inertia, for it is used for the cantilever beam, which in simple words we can tell how much structure bends under the given load. Larger the load or beam length, greater the deflection. Common causes of failure. The common causes of failure in aircraft can be summarized as human error, primarily pilot error, poor decision making, procedural errors, and lack of awareness, fatigue. Mechanical error, engine malfunctions, structural fatigue, system failures such as hydraulic or instrumental failures. Maintenance error, improper repair, skipped inspections, incorrect assembly, adverse weather, icing, severe turbulence, low visibility or thunderstorm. Air traffic control error, communication breakdown or separation failure, design or manufacturing defects, systematic flaws in aircraft design, external factor such as bird strike or runaway incursions. Here are some case studies of the aircraft crashes. First one is de Havilland Comet crash, which had occurred in 1954. It was the first commercial jet airline crash due to the fatigue failure around the square windows, which means the aircraft had the square windows. So the repeated pressurization cycle caused crack to the prop gate, which resulted in explosive decompression in the mid-flight, as you can see in the image below. So the reason was because of the square windows. And now lesson V. So in day-to-day nowadays aircraft, the windows are in round shape, so stress testing were introduced. Case study 2. Ahola Airlines Flight 243-1988. The Boeing 737 suffered fuselage rupture mid-air. Fatigue crack at the rivet joints due to repeated pressurization, as you can see in the image. The cabin rooftop tore off and aircraft landed safely with one fatality. Lesson is regular inspection and NDT critical. Case study 3. Space Shuttle in the Columbia 2003. The wing leading edge damaged during the launch. On re-entry, extreme thermal and mechanical stresses caused breakup. Example of combined stresses and deflection and thermal failure. The lesson is importance of material testing and damage assessment. Preventive measures as we can take is use of composite materials like carbon fiber, which is strong and light, round edges to reduce the stress concentration, and regular NDT inspection for cracks and fatigue. Vibration and fatigue testing in design stage. Maintenance after flight hours has detected or hidden damage. Conclusion is stress and deflection failures have led to a major aerospace accidents. Each disaster taught valuable lessons in design, testing, and maintenance. Understanding solid mechanics is crucial to prevent such tragedies. Engineering safety is built upon the lessons from the past. The reference I took about the cases were from the NASA, Wikipedia, and some of the books. Thank you.